Morning. We're going to talk about birefringence. Simply put, birefringence is an optical property. The property basically says when light travels through a material, it will split into two rays as it passes through. It's also known as double refraction. As you can see, we have a crystal on a piece of graph paper. And if you look through the crystal, you see two sets of grids instead of one. There's only one set of grid under that, and the image is splitting. Birefringence occurs because there are different indexes of refraction in different directions. One index of refraction leads to a wave called the ordinary ray or the fast ray. Ordinary ray is the one that passes through the lower index of refraction. So the pencil under the crystal that's contiguous with the rest of the pencil, what I'm pointing to here, is going to be the ordinary path for the light. This second image here is going to be the extraordinary ray or the slow ray. All right, birefringence comes from two places. Birefringences will come from ambient conditions, temperature fluctuation in, say, a fiber cable, or unintentional physical stress placed on a fiber will both cause some birefringence. We can induce birefringence by putting light through a crystal or intentionally stressing a fiber. The induced birefringence is usually stronger than the ambient birefringence, so the induced birefringence will overcome the ambient birefringence. At first, it seems like a bad idea. We're splitting a ray, so the energy would be split between the two. But we'll learn that we bifurcate the beam to polarize it into two polarized beams, which are orthogonal to each other, meaning making a right angle with each other. All right, what's polarization? Well, the sciencey definition is how light's electric field orientates with respect to the plane perpendicular to the direction of travel. If you look at the following diagrams and think about it a bit, you can think of forcing light to vibrate in a given direction. All right, so if we take a look at the figure on the right, we see that the green wave, let's call that the ordinary wave, is oscillating vertically, whereas the extraordinary wave, call that the blue wave, is vibrating on a plane perpendicular to the vertical and the horizontal. This is an example of birefringence. We see the same thing here where an instant light comes in, the light gets split because of the two different indexes of refraction. And we have the O ray paralleled horizontal and the E ray polarized vertically. All right. So where do we use polarization? Well, in free space optics, which is communication over light waves, it's a wireless communication. It's used in computer networks and defense communications. Researchers are working on a scheme to use polarization for multiplexing using iridium-doped amplifiers. All right. Optical equipment that we use in telecommunication is sensitive to polarization. Modulators, switches, and detectors all exhibit polarization sensitivity. If a A stable, well-defined polarized state is crucial for optimal performance in these equipment. If there's variation in the polarization, i.e. it's just ambient, therefore random, can lead to reduced efficiency or even malfunction of the device. So to get rid of the ambient, what we're going to do is to induce polarization. In dense wave division multiplexing, the channels can be further subdivided based on their polarization state, doubling the number of channels. In wave division multiplexing, without strong polarization, the polarization state of one channel can couple to another, transfer energy between the two, leading to crosstalk, which will impair signal quality. All right, there is such a thing. If we're inducing polarization, we have to make sure that it doesn't deteriorate as we send it down the line. So there are polarization maintaining fibers. These maintain consistent polarization throughout the system. PM fibers are a special type of single mode fiber designed to maintain polarization. They're often used in telecommunication, connect the laser to a modulator, again, because the modulator needs polarized light as an input. Polarization maintaining fibers are more expensive and have a higher signal loss, so they're not commonly used for long hauls. We also use them in the manufacture of lasers and amplifiers so that the output is stably polarized. Here we take a look at three different shapes of fibers. Basically, they put material or on doped glass. Or on doped glass is the dark gray. And what will happen is this will shrink more when the fiber cools. This causes tension in the fiber, which will induce birefringence, which will produce the polarization we want. So in summary, many telecommunications components require polarized light. Polarization assists in dense wave division multiplexing and free space optics. Polarization is often achieved through birefringence. Birefringence splits lights into two different polarized beams.